So before I actually start my talk proper, let me tell you quickly what these two topics are about. And first, when I talk about a quantum measurement, what I actually mean is a POVM, so a positive operator valued measurement, a measure. And those are compatible if they arise as marginals of a common POVM, a common measurement. And this is important because only measurements which are incompatible can actually violate Bell inequalities, for example. So this is of interest if, for example, you want to do some quantum cryptography, you need those kinds of measurements and not like something which is compatible. And as you can see this as a resource for quantum information tasks, similar to entanglement, for example, you can ask about how can we quantify these resources. And one way of doing this is by just looking at the noise needed to destroy incompatibility in a given set of measurements. Then you can say, okay, this was the amount of noise, the amount of incompatibility there was to begin with. So this was one side of things. Free spectrahedra are objects which arise in convex optimization as relaxations of linear matrix inequalities. If you don't know what those are, think about a dual STP and of a solution set to this dual STP. And then sometimes you want to know when one of these sets sits inside one other of these sets. And this is a hard question. So instead of looking at free spectrahedra, which are these, you can consider free spectrahedra instead, for which this problem becomes easier. And later we will see something which are inclusion constants, which quantify the error you have made in making the problem easier than the original problem. And the aim of this talk is to connect these two problems, more specifically to connect the problem of joint measurability of a certain set of measurements to an inclusion problem of free spectrahedra, and to connect the inclusion constants to noise robustness. So this is what expects you in the next 25 minutes or so. Right, so instead of giving you a proper definition of what compatibility actually is, let me show you an example instead, and then it will be clear what the general definition looks like. And the example is just two measurements which are binary, so they have two outcomes, 0 and 1, for example. And in the rest of the talk, we will be mostly concerned with binary measurements. So these measurements are E and identity minus E and F identity minus F. And now we assume that there's another measurement which has 4 outcomes given by this Rij. So this has two indices, I and J, which are between 0 and 1. And now we want that this R measurement has a certain property, which is this marginal property. So we want, for example, to fix the first index to be 0, and we sum over the second one. Then we would like to get back E, so the first element of the first measurement. Same if we fix the first index to be 1. We want to get 1 minus E. And now if we fix the second index instead and we sum over the first, we want to get F and identity minus F. So this is what I mean when I say the original measurements or the compatible measurements arise as marginals of a common measurement. This common measurement then being R in this case. And then if such a POVM exists, then we say that the measurements are jointly measurable or compatible. That's the same thing. You can pick the term you like better. And for concrete STPs, this is a problem we can, for concrete measurements, this is a problem we can solve using an STP. So somehow this is computable. If you have more measurements, you get a POVM which has more indices, and you always fix one and you sum over the rest. So this is how this generalizes. And if you don't like this definition because it's kind of abstract and there's no operational interpretation, there's an equivalent one which says that E and F are compatible if and only if they arise by classical post-processing from a common measurement R. So this is maybe a more concrete interpretation. Now, it's known that there are incompatible measurements, and it's also known that measurements can be made compatible if you add a sufficient amount of noise. So what does adding noise mean? It means, for example, if we're still with binary measurements, that instead of measuring the element E and identity minus E, you measure a convex mixture of this E, so S is between 0 and 1, with a fair coin, identity over half. So some part of the time you're actually performing the measurement, and some part of the time you're actually just flipping a coin, and depending on the outcome, you just output 0 or 1. And we can generalize this, or we can look at how much noise we need to make a set of G measurements in dimension D compatible. And this is what this set gamma is about. So these are the noise parameters S between 0 and 1 of length G, such that no matter which measurements you pick in dimension D, so these are these E1 to EG, then if you look at the noisy measurements with this amount of noise, they are compatible. And as I said before, incompatibility is a resource for quantum information tasks. So this set gamma tells you how much incompatibility there is in G measurements in dimension D. And, well, this quantifies the amount of noise robustness. So this is something which is relevant for application and somehow tells you something about your theory. So this is the object which we would like to study in this talk, and the aim of this talk is to give upper and lower bounds on the set gamma. And what people have done before to get lower bounds is basically most approximate cloning. So instead of measuring several measurements on the same state, which are noisy, you could come up with the idea that actually what you could do is you take that state, you clone it. Of course, you cannot do it perfectly, but a noisy clone would be fine. And then you just measure on the clones. And these views are somewhat dual to each other. And that's one way of getting lower bounds on this gamma. And what we will do is to get lower bounds in a completely different way, which are then better than those you get from cloning. Let me give you an easy example to give you some intuition about the set gamma. So give you a point which is actually in there. And one point which is in there is this point which has noise 1 over G, so 1 over the other amount of measurements everywhere. Why is this true? Well, I mean, first, if you look at the definition of the set gamma, you might or might not see that it's a convex set. And then we only need to argue that, for example, if we take G equals 2, so only 2 binary measurements, that if we measure only one of them and we flip a fair coin for the other one, that is certainly something we can do. So the points 1, 0 and 0, 1 are definitely in the set gamma. So if we take the convex combination of those 2 points, we end up with 1/2, 1/2. And this is exactly how you get this 1 over G there. So it's a very easy argument to see that this dark blue region is in the set gamma. So this triangle is always in there. But we're interested like if there's something more to that. So is there a light blue region which is also in the gamma, which is like non-trivial? So this was the part about joint measurability, like in a very brief introduction. So let's now talk about free spectrahedra. And let me give you the definition of what a free spectrahedron is. So a free spectrahedron is defined by a tuple of matrices, of D by D matrices A. So it's a vector with elements A1 to AG, and those are D by D matrices, which are self-adjoint. And then those define a set. If we consider all the matrices X, which are all tuples of length G, of n by n matrices, which fulfill the following inequality. This AI tensor Xi, you sum over I, and you require that this sum is smaller or equal than the identity. And this gives you the free spectrahedron at level n, because n is the dimension of the matrices X you allow. And then the free spectrahedron proper is just the union of all these different levels. So how you could think about the set is you look at this linear matrix inequality up there, so the sum over the AI tensor Xi, and you don't care too much about the dimension. You just say, I want all the matrices, no matter what the dimension is, which fulfill this linear matrix inequality. And one comment, which will be relevant later, usually if you fix the first level, so just scalars, of this free spectrahedron, there's more than one free spectrahedron which has this first level. And this we keep in mind to use later. So let me give you a concrete example of a free spectrahedron which we will care about in the rest of the talk. And that's what people have called the matrix diamond. So it's not our name, unfortunately, because it's a very cool name. And it's given, again, at level n, as n by n matrices, and a tuple of those of length G. And now we require that no matter which sign epsilon I, so epsilon I is either +1 or -1, is in front of these xi, that those sum to something smaller or equal than the identity operator. And this has to be true for all signs you could put there. So there's 2 to the g different constraints. And if we now draw this at level 1, so I just put g equals to 2 again, and this is the first level of this. So this is just the L1 ball, because as you can see, these are just the vectors which have entries that if you take the absolute value of those entries and you sum them, you get something smaller or equal than 1. And this is why it's called the diamond, because this looks like diamond-shaped somehow. And as we can see, it's a polytope which has 4 extreme points. And now you can say, wait, I mean, there's no epsilon, there's no AIs here. Where are they? It doesn't really look like what I've shown you before as a definition. But of course, you can take all these constraints and you can just write them on the diagonal of a matrix, such that you get on each line of these 2 matrices, you get all the different sign combinations. So you get 1, 1 in the first line, 1, -1 in the second line, -1, 1 in the third line, and -1, -1 in the last line. So these are all the 4 constraints you have here. And if you now tensor with the xi's, then you exactly get that you have to fulfill all these different sign combinations. So now you know what a free spectrahedron is. There was also something about inclusion in the title. So what does that mean? Well, first, if I say that a free spectrahedron dA is included into 1 dB, what this actually means is that you look at all these levels and you say that the nth level of dA is inside the nth level of dB for all n. And now there's a lemma by Helton and others which connects this to positivity properties of a special map. So assume that you're given 2 free spectrahedra, one by A, which is given as capital D by capital D matrices, and the other B, which is given as small d by small d matrices. And now you look at the following map. You look at this, you assume that the first level of the dA is bounded. That's the technical condition you need. And now you look at the unital linear map phi, which is defined on the span of the identity operator and A1 to AG. So on the operator system generated by A1 to AG, if you know what that is. And it maps to D by D matrices. And what it shall do is, of course, it maps the identity to the identity because it's a unital map, and it maps AI to BI. So that's a well-defined map if you, for example, assume that the AI and the identity operator are linearly independent. And then this lemma shows that this map is n positive on this operator system if and only if dA is in dB at level n. So this also shows that inclusion at level 1, so level 1 is the usual spectrahedron, is hard because you would have to check whether this map phi is positive, that's NP hard. But if you want this for the free objects, then this is inclusion for all n. So this means this map has to be n positive for all n, so completely positive. And complete positivity we can also check using an SDP, for example. And this is why, like, the free problem is a relaxation of the problem at level 1. This is where this comes from. And in general, of course, if you have inclusion at the free level, then you have also inclusion at level 1, but the reverse implication is not true in general. So if you know that dA1 is in dAB, that doesn't mean that dA is in dB, but you can make this work if you shrink the set on the left-hand side a bit. And we can shrink asymmetrically if you want, so we shrink x1 by a different amount than xg, for example. And we can also define the inclusion set for which this works. So now we fix a dA, and we fix dA to be the matrix diamond. And now we ask, okay, we want all vectors with entries between 0 and 1 of length g, such that if you pick some tuple B of D by D matrices of length g, if you have inclusion at level 1, this implies that if you shrink by this amount of S in this delta, then the inclusion at the free level, so D matrix diamond is inside dB, is also true. So this is the set of parameters which make this implication level 1 for the matrix diamond implies like smaller free level true. And later we will find that this inclusion set delta is the same as the compatibility region gamma, if we define this correctly. Well, so now I've told you about two different problems which don't have much in common, on the first side at least. And now I will connect these two problems, and this is the main result of our work. And remember, we're still talking about binary measurements. And I will only tell you in the end what you would have to modify for this result to have more outcomes. So you pick you get a tuple of G D by D matrices, which are again self-adjoint, and we call them E. And now as a shorthand, we just write 2E minus I to be the vector which has 2E1 minus the identity operator at the first entry until 2EG minus the identity operator on the last entry. And now we can look at the inclusion of the matrix diamond at level 1, so the L1 ball, into the first level of the free spectrahedron defined by this 2E minus I. And this turns out to be equivalent to the property that E1 to EG are POVM elements. That doesn't mean that they have to belong to the same POVM, but they have to be matrices which are smaller equal than the identity operator and which are positive. So they define binary measurements. So that's nice. If we now go to the free level, so to the inclusion of the free spectrahedron, the matrix diamond into the free spectrahedron defined by this 2E minus I, this is equivalent to the E1 to EG to be jointly measurable or compatible POVM elements. So this means the binary measurements defined by those are jointly measurable. So this gives you something more. They don't have to be only positive and smaller equal than the identity, but they have to be jointly measurable as well. So inclusion of the free objects is stronger than inclusion at level 1, as it should be. And now you can ask, okay, I have now the first level and I have the free level. What about the intermediate levels? And if we now look at the inclusion at level K, K between 1 and D, this is equivalent to the fact if you take an isometry from dimension K into dimension D, any isometry, and you look at the compressions of these matrices E1 to EG, so at V star E1V until V star EGV, those are jointly measurable POVM elements. So let me rephrase this. You have these D by D matrices, you look at a K corner or any K corner, K dimensional corner of these matrices. If they are POVM elements, they're still POVM elements if you just look at the corners, and they look compatible if you just see K dimensions, but they might not be compatible if you look at all dimensions at the same time. So this inclusion of the different levels really gives you like a hierarchy of being more and more compatible the higher you go. So we have now identified inclusion with joint measurability, but we can do more. We can also identify this compatibility region gamma with the inclusion set delta. So the compatibility region were the noise parameters which make any G measurements in dimension D compatible, and this inclusion set delta was that the parameters would say, okay, if we know that the matrix diamond at level 1 is inside a free spectrahedron defined by a tuple of length G and of D by D matrices, then inclusion at level 1 implies inclusion at the free level if we shrink by this objects in S in delta. Sorry. So before we go on and exploit the last equivalence to be or to learn something about gamma, let me give you a quick intuition of how you would prove this. So the first point is actually quite easy because you see at level 1 we have just the L1 ball, so we can just check the inclusion at extreme points, and then it turns out that this is exactly what you have on the right-hand side. For the second point, you have to use this map phi, that's why I introduced it. And this map phi, as I mentioned before, acts on these objects which define the matrix diamond and map them to this 2EI minus the identity operator. And the inclusion holds if this map is completely positive. And now you can use Arbeson's extension theorem and find that phi is completely positive if it has a positive extension to C to the 2 to the G, since all these elements on the left-hand side are diagonal, so it's in a commutative algebra, and their complete positivity is the same as positivity. And then you can just write down a basis g eta of this c to the 2 to the g. You can define capital G eta to be the image of this basis elements under phi tilde. And then it turns out that this is a joint POVM for E1 to EG if and only if this phi tilde is positive, and this was if and only if the inclusion holds. And that's basically how you prove this. So let's now use this connection, which we have found as a second theorem, to learn something about the compatibility region. And if we look in the literature, we find that there's a point, which we already know, in this set delta, which is independent of D, which is exactly this 1 over G, which we have seen before using arguments from quantum information. But there's also a point which is independent of G, so independent of the number of measurements, and only depends on the dimension, which can be found in this work by Helton and others, which, well, at least I don't know how I would argue this from quantum information, and as far as I know, this was not known before. So this actually gives you something new here, and it just exploits the symmetry of the matrix diamond. So now we have 2 points, but we would like to have more. I mean, the set is large. So we look at a different work by Passer and others, and they really consider the matrix diamond. Everything before was valid for a larger class of free spectrahedra. And they show the following. So if you fix G and D to be integers, then they show that it holds that this set QCG is inside delta. And QCG you can find below. That's just the positive part of the L2 ball. That's why we call this QC quarter circle somehow. And so this means that if you take a G-tuple E1 to EG of maybe POVM elements, and you take any positive vector S which fulfills this, so which has Euclidean norm smaller or equal than 1, then if you look at the noisy elements, so at the mixture with white noise, those we will jointly measurable. And what's even better is that there's a converse to that. So if G is larger or equal than 2, and you have D larger or equal than 2 to the ceiling, G minus 1 over half, so the dimension is exponential in the number of effects, then the reverse inclusion is true. So we have delta inside QC. We can also give the maximally incompatible measurements corresponding to that. This is a recursive construction, and it works like this. You take everything we had before, you tensor sigma or the Pauli X to it, and you add Pauli Y tensor identity and Pauli Z tensor identity. And so let me walk you through some examples. So for k equals to 1, this is just Pauli X, Pauli Y, Pauli Z. Those are known to be maximally incompatible. Of course, those are not POVM elements, but these are the observables corresponding to the POVM. So to get the POVM elements, you would have to consider identity plus F over half and identity minus F over half. And at level 2, you take everything you had before, tensor Pauli X to it, and you add Pauli Y tensor identity and Pauli Z tensor identity. So now we can collect everything we have learned about gamma so far in a phase diagram. So you have G on the x-axis and D, the dimension, on the y-axis. And now you have 3 different regions. The green one is the one where we actually know what gamma is. Gamma is this positive part of the Euclidean ball, because the lower bounds from Passer, the lower and the upper bounds from Passer et al. Coincide. We have this orange region down there, where we know that the set gamma, which we're interested in, is strictly contained in the quarter circle, because the point by the Helton paper, this 1 over 2D, at this point goes outside of this quarter circle, but we know that it's in gamma, so gamma has to be strictly larger than the quarter circle. And for the blue region, we just know that the quarter circle is included in gamma, but we don't know if it's strictly larger or not. But if you take the bounds you get from this quarter circle and the bounds you get from this 1 over 2D, this is better. Like if you look at the diagonal of this quarter circle, so 1 over square root of G, this is better than symmetric cloning, at least. So here we get something new, exploiting this connection, which does more than this idea from symmetric cloning. And, well, I mean, it has to be noted that this gamma, of course, shrinks with G, but so the orange region just means that the quarter circle shrinks faster with G than the gamma. So let's look at what we would do for more outcomes, because everything we have done now was for binary measurements. So the matrix diamond is the object which we have to consider for inclusion for binary measurements. So the question is, what do we have to consider for k outcome measurements? And we will just reinterpret it, what we have actually done here. So if you have a binary measurement, you can associate it with outcomes plus, minus, and 1. And you can associate a simplex with these endpoints to that. So it's just a line with endpoints plus, minus, 1. And now if you take the direct sum of these two, of the simplex with itself, which means just embedding plus, minus, 1 into higher dimensions, so plus, minus, 1, 0, 0, plus, minus, 1, and taking the convex hull of this, then you get back the matrix diamond at level 1. So now let's take this recipe and apply it to k outcomes. So for k outcomes, you take the k-1 simplex, you take the direct sum of all these objects, and now we have to build a free spectrahedron on top. And the matrix diamond, I mean, the free spectrahedron on top is not unique, but the matrix diamond is the largest one that you can put on this L1 ball. So if we also take the largest one and put this onto this new object, we get something that we have called the matrix jewel, because it generalizes the matrix diamond. And now if you look at this object and you redefine delta and gamma accordingly, then you can recover exactly the same two theorems. So inclusion is the same as being longitudinally measurable, and gamma is the same as delta for k outcomes. And you can also study similar inclusion problems for quantum channels, and you can study them for generalized probabilistic theories. But this is ongoing work, so I cannot really say much about this, at least not yet. And so let's wrap up. So what we've seen today was we have seen that the compatibility of binary POVMs corresponds to the inclusion of the free spectrahedron, which is called the matrix diamond, into the free spectrahedron defined by the POVM elements, so by this 2e minus I. We have seen that the compatibility region gamma corresponds to the inclusion set delta for the matrix diamond. And we have seen that if we are in the regime where the dimension is exponential in the number of measurements, then we know what this inclusion, what this compatibility region is, and is the positive part of the Euclidean ball. And if you want to know more about that, I can give you two references. The first one deals with the binary outcomes, with binary measurements, and the second one deals then with the general case. But I would recommend first reading the first one and then the second one. So thanks for being here. Thanks to the organizers for this very nice conference, and I'm looking forward to questions.
So questions.
So my question is about the motivation for the compatibility region, because you adding white noise, but we know, for example, in entanglement theory, we adding any separable state to make the state separable. So why not considering here adding any compatible measurements and defining similarly a compatibility region in this way?
Yes, this is actually what people usually do in this, if they work on joint measurability, that's right. The reason we have considered this problem is because here this nice correspondence to free spectrahedral inclusion holds. You always get this, I mean, you can also get something different. You can get basically A times the identity, or AI times the identity, if you want, but you always get a fixed trivial observable somehow, which mixes with your measurements. So if you really would like to consider like mixing with every trivial measurement, then you would have to do something new. But I mean, those things also give you bounds on compatibility. And somehow, I mean, it depends on who you ask. I mean, people have also considered this white noise model before, because it's natural that the noise is not biased. You can also consider noise models where you have trace of the objects over the dimension times identity. And we studied some of these alternative noise models and saw what we got in this first paper here. But yeah, I mean, the honest answer is we study white noise because there this inclusion works best somehow.
Okay, so the bounds that were obtained from cloning, I mean, they have a nice operational interpretation from both sides. One, that no cloning prevents you doing any better, and then achievability, because we have a protocol then that can achieve it. So can you have any other kind of an operational interpretation for your tighter bounds? Either a new insight into what's the upper bound, what is stopping you going further, and then from the other side, what does the protocol look like that achieves does better than symmetric cloning?
That's an interesting question. The short answer is I don't know, because I mean there's no actual task you want to perform here. Of course, you want to jointly measure this, and you can say, okay, these bounds just mean that there are objects which are more incompatible than you would need for cloning. But I don't know of any concrete operational interpretation for these new bounds. It's just that
on the achievability that you get a measurement that you could then classically post-process. So to get the marginals. So what does that measurement look like?
I mean, these were
the cloning region. Sorry.
These were the measurements I've shown you before. This recursive construction by just tensoring with Pauli's and adding Pauli tensor identity. This just means that if you want to measure those and you want to have a measurement which gives back these measurements, or a joint measurement which gives back these measurements by classical post-processing, you have to add that amount of noise. That's what it is. But so it's somehow compatibility is less than cloning. I mean, cloning is somehow overkill.
Maybe this is related. In the proof of your main theorem, at some point you were showing how you take this set of POVMs, and if the condition of inclusions is right, you can actually construct a joint measurement. But we are constructing this using an extension of a positive map from operator system. That extension is not explicit, right? So this is just like an existence result. You don't really have a way to construct this joint measurement.
Yes. Yeah, it's also because these joint measurements are usually not unique, the same as this extension is not unique in general. But yeah, I mean, in principle, I mean, you could try to compute an extension by just picking your joint measurement and saying, okay, this is my map, this is my extension. Or if you have a valid extension, you also get the joint POVM from there. But you're right. I mean, usually it's not constructive.
So I mean, this is related to the previous question. One is the question of whether, like this, does this give you any insights about uniqueness of the joint? That's the first question. Maybe you can answer it.
Yeah, I think it's easier if I answer now, then I don't forget your question. No, it doesn't. I mean, some for concrete problems, it's not clear that this gives you an advantage, because I've just exchanged one problem which I can solve using an SDP by another problem which I can also solve using an SDP. So the advantage of this treatment is that it shows you generally, if you consider G measurements of dimension D, then it tells you how much incompatibility there is in this for these parameters. But for concrete observables, it doesn't really give you something new.
Yeah, I just meant like conditions for when a given set of POVMs admits a unique joint, like not necessarily. Yeah, but the other one was about like if I give you 3 POVMs and they are incompatible, but it happens that every pair is compatible, then what does that look like in terms of inclusion of spectrahedra, like the free spectrahedra?
Well, I mean, you could write down the corresponding spectrahedra, which are just slices of your original spectrahedron,
right?
Which then corresponds to your like pairs of spectrahedra are compatible. But I would need to think longer about how this actually looks like.
Okay.
Thanks. Just a comment. I think the free spectrahedra are closely related to the properties of the free groups, and Paulson PZ worked on those. So in particular, there are some estimates how different the infinite dimension from the finite dimension is. There are some constants, this exactness constants, that can play a big role.
Yeah, it's also, I think it's discussed in this paper by Helton and others, where this 1/2D comes from. They discussed that this is related, but apparently not exactly the same problem. And also the other paper by Davidson and others, they work in infinite dimensions, And yeah, so if you want to know more about this, this is maybe a good place to look.
Okay, so let's thank the speaker again.